Just
you can't run things. Okay.
well, you're lucky that it's stable. Mine is really so
Yeah.
code.
Shorts. It calls for the first really nice day for them.
Yeah.
I can wear them at home. I can't wear them coming up to school. It's like a 10, 15 degree difference.
Right. Sucks.
Start getting dressed in the morning, then I gotta rely on my phone to check the weather up here before I get dressed.
Yeah, it's pretty dramatic.
It's like a whole different climate in there.
Where do you live
Do you know where Lindsay Creek is?
Yeah.
So I live in a new development just up above Lindsay Creek, almost at the end of the road. Yeah. Yeah, actually, do you know where PCI has done the restoration down there, in there?
No.
No, okay.
So I should check that out.
Yeah, they're, just minorly restoring the little bottom of the canyon there. So you get probably
But it was
3/4 of the way up the road.
it's all the time.
And then I take a little dirt road up onto my hill where they're broken. Yeah.
Quiet spot. Am I good?
Yeah.
Oh, so
She was not in my last class.
I do not know, and I kind of doubt it. She has not been well.
I don't.
Yeah, she wasn't in my last class, but she's worked through it.
Like when you first.
Last I heard, it was
Yeah,
none of us was that.
Not
Yeah.
There's definitely a bit of that going around. Steve's down from the count too. Yep. Stay well.
For our
Yeah,
posters
it's the
tomorrow.
heater. What are you meaning?
Do we need to turn that in at the beginning, or are we gonna have that class period to?
You'll have that class poster. Yeah. No. I hate to even ask for it now this week, but we just have to get that.
Making sure that I still have
Making sure we have it in hand when it's time. So tomorrow, speaking to all of you, we'll be back in CNR for another work session. Our last work session. I mean, obviously, you and your groups can continue working on your own time. This is our last in-class session. And you will be turning in your poster on a thumb drive by the end of that session, or at least by the end of that day. Please make sure that you get multiple eyes on the posters so that they're well edited before taking the print. I know this is kind of a rush job, but trust between you and your team members, you'll be able to whip it into shape. Does anyone have any questions about that? Okay. Yeah, and so a reminder that next week is exclusively a all-day field trip. Okay, so you and your team members are welcome to meet during our regular times, but the only time you'll see me is all day Thursday, 9 a.m. At our usual pickup spot. And I think Steve indicated I should recruit you fully to help drive, so I'll get in touch and we'll grab the vehicles right beforehand if you're available. Yeah. Great, thank you so much. And that will be with the Latah Conservation District. And yeah, it'll be great. Hopefully, we'll have a day like this. Too long. I'd say odds are not in our favor, given our track record. But, it's going to be a fun day regardless. And you'll want to bring boots, appropriate footwear for getting muddy, and lunch, just everything you need for the day. So that'll be fun. That's next week. All-day field trip on Thursday.
Yeah. And if I remember correctly, these are due right after that.
Yep. Yeah. So before you all walk away from the vans, I'll just collect your journals. Make sure you have them there with you. That way we can get those graded before the end of the term. And you will have an opportunity to practice your presentation the following Tuesday with Steve. Steve's not able to come on the trip, but he will work with you all on your presentations the following Tuesday. That's what we got coming up. It's a really rapid push to the end. So hang in there. I know you all got lots going on. Come on up front.
Come on down.
Good to see you. Are you feeling better?
Trying to.
Wow. 1, 2, 3, 4, 5, 6. Pretty much a full house. That's great. Thank you all. Greg? You ready?
Yeah, I'm all set.
Okay. So, Greg, this is our environmental project management class, or almost everybody. Most are seniors or grad students. The seniors are finishing up their natural resources and society track here at UI and getting ready to move on to other things. And we have been doing our best to equip them with a skill set that they'll be able to put to work immediately, whatever they end up doing next. We just talked to Brian on Tuesday about, yeah, it was fun. We talked to Brian about what it's like to work within a nonprofit, specifically TNC, of course, and he was able to share some of his work with us, which was great. Today, we're looking forward to hearing more about your stuff. Everyone, this is Greg Snedden. He is an old friend, and he is a USGS research ecologist in Louisiana. Specifically, he works at the Wetland and Aquatic Research Center there. And there's a lot of exciting things happening down there with respect to the delta restoration that I'm not even aware of, so I'm really looking forward to getting up to speed. And Greg, if you would at least start by telling us about your professional arc, that'd be great. How you came to do what you do, and then we'll walk us through the slides. And if it's okay with you, we'll just ask questions throughout, kind of informally.
That'd be great. I prefer that, actually. So that's perfect.
Good. All right, we'll take it away.
All right. I'm Greg Snedden. As Micah said, I'm a research ecologist with the USGS Wetland and Aquatic Research Center down here in Louisiana. I've been with the center and the survey I just got my 10-year service award last fall, and I'm not quite sure where all the time went. But anyways, just to I'll just kind of back up to education and experience a little bit to, as Micah said, give you an idea of what my professional arc has been, and it's been kind of windy. I grew up in Illinois, central Illinois, and I got a bachelor's degree in ecology from the University of Illinois, focusing on aquatic ecology and fisheries. And after finishing my bachelor's degree, I moved down here to Baton Rouge for graduate school at LSU in their fisheries program. And for my master's work, I did radio telemetry on spotted gar, which maybe you're not familiar with gar, but they're a very primitive fish that are found predominantly in swamps and wetlands and in subtropical climates. I radio tracked them in the Atchafalaya River Basin, which is the largest bottomland hardwood swamp in North America. And after finishing up there, I got a job with the state of Louisiana where I worked for about 3 years as a monitoring biologist working on restoration projects down here, primarily Mississippi River diversion projects, which I'm going to talk about extensively today. And after 3 years with the state, I went back to school, back to LSU, and enrolled in their oceanography PhD program. And that's where I met Micah years ago and continued working on river diversions there, specifically focusing on how river diversions affected coastal hydrology in terms of sediment transport and water level and salinity fluctuations, and how all these things kind of intermixed with other drivers of these processes like coastal ocean conditions and things like that. And I finished that in 2005 or 2006, and then did a postdoc at UNC, University of North Carolina, Wilmington, where I looked at river plume dynamics at the mouth of the Cape Fear River. And after completing my postdoc, I came back to Louisiana, where I started with the survey and have been there ever since, and still continue to this day, largely working with these big Mississippi River diversion projects. So I'm going to talk a good bit about that today. So kind of the arc of this presentation, I'll give you some background on kind of the coastal geology of the Mississippi River Delta Plain and how and when it was formed, and by what processes, and then I'll kind of get into why this landscape is so important and what's happening to it today in terms of deterioration. And then I'll get into some of the restoration activities that are either underway or being planned, and present a few tidbits of how some of the research that I'm doing at the center is being integrated into restoration planning and management. So with that, I'll get into the first slide. Can you guys see my cursor moving around?
Yep.
Yeah.
Good. That's going to be a tremendous help since I don't have a laser pointer strong enough to reach Idaho. So, all right. Oh, there we go. All right, so I'll just kind of zoom way out and just show you guys the Mississippi River drainage basin. It drains about 41% of the continental United States, which includes 21 states and two Canadian provinces. And you can see over here it even captures a little bit of Idaho water. And it drains about 1.2 million square miles or so of the continental United States and a little bit of Canada. And along with the water that it discharges, it conveys a whole bunch of river sediments. And you can see those river sediments here. This is a MODIS satellite image of coastal Louisiana, and you can see this is the Mississippi River coming down here, the main stem, and there's a big plume, sediment plume right here. And then over here, this is the Atchafalaya River flowing through the Atchafalaya Basin, and then it discharges through two channels, the Wax Lake outlet right here, and the main stem Atchafalaya River right here. And again, in a pretty prominent sediment plume right here. So it's this sediment discharge coming out the river that's created this whole landscape that we call the Delta Plain over on the southeast portion of the state. And so this Mississippi River isn't static. You can see this kind of traces the different courses of the Mississippi River over the last 2,000 or 3,000, 4,000 years or so. And so I think there's one more. Yeah, there we go. So, and this doesn't even show all of them, but you can see it basically over the last several thousand years, it almost behaves like a garden hose that you would just turn on and turn loose in your backyard, kind of switching back and forth every 1,000 years or so to find a more efficient course to the river and or to the sea, excuse me. And so in doing so, it deposits a lot of land or a lot of mud on its flanks, and they get reworked by tides and winds and things like that to form mud flats, which become colonized by vegetation and ultimately turn into wetlands. And so there's a geologic cycle associated with this that we just kind of call the delta cycle down here. And you can, this figure here is just a schematic of what it looks like if you plot the delta land area on the vertical axis versus time. and each time the river changes course, it becomes basically a fluvially dominated system with increasing river and sediment discharge coming down the river. And as that happens, more and more land gets created, but the hydraulic gradient also begins to decrease, which slows the flow down and makes, over time, it becomes a rather inefficient route to the ocean. And it'll reach this point where it'll find a weak spot in its bank and bust through. And these events are called avulsions. And then it will somewhere around right here in the delta cycle, it will switch course and abandon the present one and start this whole cycle over again on a new course. And the old delta lobe then goes through a period of deterioration where it's no longer being subsidized with sediments anymore, and tidal action and hurricanes and things like that begin to erode the sediments and drag them back out to sea. And as a consequence, the land area begins to diminish. But that's historically speaking, that's always been okay, because there's been a new part of the delta then beginning to grow somewhere else. And so over time, this just kind of shows all these different delta lobes that have happened. I just got a little message that said my internet connection has become unstable. So let's all cross our fingers. I don't even know what that means. But over time, we get these different overlapping delta lobes that are of different ages, and together they all form what we recognize as coastal Louisiana today. All right, and so there's kind of classify we classified these landscapes a million different ways, but one of the ways we classify them is either being active or inactive. And the active deltas are that's shown on the left here, and these are sort of the front end of the delta cycle where things are growing and the river's emptying into the coastal ocean, and these dendritic landscapes begin to form from sediment deposition and things like that. And these regions generally have high water levels, high rates of sediment deposition, and then flood-tolerant plant species. Down here is a picture on the ground of the Wax Lake Delta, which is shown in the aerial photograph up here. And this is American lotus, and this plant can be flooded almost pretty much permanently, and it will do just fine. It's adapted for these kinds of conditions. It's kind of a colonizer species in the delta cycle. On the right, what we have is part of the delta that we call the inactive delta, and these are the regions that have been abandoned by the river, and they tend to be dominated by other species that are considerably less tolerant, like Spartina patens, Spartina alterniflora. Those are brackish and saline wetland plant species. And they're wetland plant species. They can handle flooding, but in general, they prefer to stay dry and have their oxygenated soils and things like that. So in the title of the talk, when I brought up hydrogeomorphic context, this is kind of what I'm talking about, and I'm going to get into some of this a little bit later in the presentation. And so these processes, this whole delta cycle, even though they over broad spatial scales with main stem river courses switching and things like that, those processes may play out over several hundred years or so, but you can actually see it happen in smaller areas over much shorter time scales, and we see the same processes happen. And so I'm going to just summarize just a great read paper that was published in Geomorphology a few years back, where they actually documented this cycle in a newly formed crevasse in the Mississippi River Delta. So this is zoomed way in at the mouth of the river, and you see all these different channels. It's flowing downstream from left to right. And this channel right here, you can see there's a break in the bank right here. And this was created in 1978. And they basically just did this with some excavation equipment just to see what would happen. in the area if they kind of turn the river loose into all this open water right here. And so what happened was they had, within 5 years, massive sediment deposition occurring. And so all these mudflats were created underwater initially, but the deposition was so rapid that within 5 years or 6 years or so, those mudflats became exposed, broke the water surface. And that's something that, when we say that, we mean we say that they became subaerial, in case I start throwing that term around. So anyway, we see these subaerial delta displays begin to manifest themselves within about 5 years or so. And then about 8 years later, you can see it's really developed, filled in, and all this area right here that used to be open water has now become deltaic wetlands that are thriving. And so what the authors of this paper did was a few things. They wanted to look at the rate of sediment deposition, so they started measuring that by taking soil cores through the water surface down through the bottom of the open water, and they measured the rate of soil deposition, or we call that accretion down here. And what they found was that initially, when the mudflats were not subaerial or exposed, breaking the water surface, we call that when they're subaqueous, when they're underwater, there was this massive infilling with accretion rates of about exceeding 21 centimeters a year. So basically each year, the depth was decreasing by 21 centimeters. And that happened for about a year or two. And these are really high rates. We don't really see these in our wetlands very often, anything approaching this rate. And then after the broke the water surface, then the accretion rates, the deposition rates slowed considerably, by over an order of magnitude, to about 1.5 centimeters a year. They also measured productivity below and above ground of wetland plant species. And prior to the delta display becoming subaerial, there were no wetland plant species. It was open water. But once it became subaerial, they observed just a rapid explosion of below ground production shown in the brown, and above ground production shown in the green as well. And eventually the productivity below ground came down to kind of more sustainable levels of what we typically see, about 500 to 1,000 grams per square meter. And so basically what they found was that the elevation of these wetlands initially was driven strongly by direct sediment deposition, of mineral or inorganic sediment deposition. In other words, particles entrained in the Mississippi River water settling out onto the bottom and piling on top of each other, and increasing the elevation of the surface of the mudflats. But after it broke the surface, the mineral sediment deposition diminished quite a bit, and then the soil development then was more dependent on production by wetland vegetation, particularly below ground production, where roots are grown, and then the plant, some of that root matter decays and turns into soil, and then that's how, at that point, that's how the elevation capital in these wetlands is maintained. So, so I probably should have been flipping through these bullets as I went through that. But so basically, we see early on, we see kind of the active delta phase with high, lots of flooding because the elevation of the mud flats is low. And then as that elevation increases, they begin to flood less, and their soil production then becomes more driven by biological processes instead of direct river sedimentation. So then drivers of vertical accretion or soil development in wetlands then is basically just the sum of the mineral sediment accumulation brought about through sediment deposition of sediment-rich river water and organic matter accumulation brought about by the production and subsequent decomposition of biomass coming primarily from wetland plants colonized on the mudflats. And both of these contributions are strongly regulated by vegetation biomass and the rate at which it's produced. And that the deposition of mineral matter is influenced by the above ground biomass, because plants will slow water flow and reduce turbulent energy of the water and dampen waves and things like that that cause the particles to be more conducive to settling. And organic matter production, organic accumulation is driven mainly by the balance of below ground production and decomposition. So early on in the delta, it's basically a physical process. It's basically hydrodynamics and particle settling dynamics. And later in the delta phase, the inactive regions, it's more of an ecological process where healthy plant communities are highly productive, and they, through organic matter accumulation, produce soil at high rates. And you can actually see this if you take a soil core, as shown here. This actually shows kind of both of these processes, where near the bottom, which is going to be the older soils, you see you can see it's kind of gray, and there's a lot of clay in here and high mineral content. And then you get above this contact point right here, and you see a lot more organic matter, roots, and things like that. So both of these occur at the same time, but early in the delta phase, the mineral sediment accumulation is more prominent, and later in the delta phase, the organic matter accumulation becomes more important. So most previous work involving accretion in wetlands, and particularly as they relate to river diversions, has focused on the mineral deposition. It's just more easily understood. It's less chaotic. Biology and ecology is just inherently chaotic and hard to model and things like that. But the particle settling dynamics are very easy to model and very easy to understand. And I think that's why historically in this line of work, the vertical accretion has largely been equated with mineral sediment deposition. But biological impacts, specifically vegetation productivity as it relates to inundation stress, which I'll get in later, has been largely overlooked. And these biological impacts may be particularly important in these inactive regions of the delta dominated by flood intolerant species. And I'll get into this business of flood tolerance in a few minutes. So the delta landscape now is in a state of deterioration where we're losing, it's been cited as high as 35 square miles a year. And it's literally just vanishing and turning into open water. And there's a lot of reasons for that. And everybody has sort of one they think is most important, but in reality, they're all kind of important. First of all, beginning around the turn of the 20th century, levees were built along the length of the river, and for flood protection and navigation and things like that. And so this whole process where the river would switch courses every few hundred years basically stopped, and we locked the river in place. And so with the exception of the regions right next to the river, the existing river course, everything is basically in that inactive, deteriorating phase. And most of the sediments are going out of the mouth of the river and then immediately into 2,000 feet of water in the Gulf of Mexico, where they can't really create any more wetlands. We've also dug a lot of canals for oil and gas exploration and extraction, and that provides direct conduits for salt water to come in. And and either stress or possibly even kill the wetland vegetation in these wetlands. And then there's this little guy. This is a nutria. This was a gift from South America. The Tabasco family thought that they would make nice fur coats, so they brought a bunch up from South America, and they love to eat wetland plants. And so we've done experiments where we'll build exclosures to keep nutria out in otherwise healthy wetlands, and then you can come back a year or so later and look at where your exclosure is, and you'll see a thriving 1 meter by 1 meter wetland inside your exclosure, and outside of it, just an area that's been completely polluted by these things. Hurricanes are obviously a big problem, well, for all of the Gulf Coast, but they have profound impacts on wetlands in Louisiana. This figure here on the left shows the Upper Breton Sound Basin that's southeast of New Orleans before Katrina in April, and then a couple weeks after Katrina on the right, and you can see it doesn't even look like the same place. Just a tremendous area of wetlands were lost literally overnight. And then finally, sea level rise. Sea level rise is a big problem in that these plants, as I mentioned, they're adapted to live to thrive in saturated soils and flooded conditions, but they have limits. And so, if the sea level's rising and the plants can maintain their elevation in that rising tidal frame through organic soil production and things like that, then that's a sustainable trajectory. But often what we have here is sea level rising much faster than the land surface elevation is rising, which basically puts the plants underwater, diminishes their productivity, and creates an unsustainable situation. So we kind of call that the accretion deficit death spiral down here. It's basically a negative feedback loop or a positive feedback loop where we have decreased if plant productivity decreases due to flooding, that results in decreased organic matter production, which decreases the vertical accretion rates and diminishes the rate at which they can keep up with sea level rise, which floods them more, which goes on and further decreases plant productivity. And this just keeps going around and around until an area that once was a healthy wetland is now pretty much just open water. So, and then just to provide a little perspective here, this delta began forming around the time written language began, and over time, this is land area over here versus time, and you can see it growing all the way to the Industrial Revolution when sea level rise became a problem, and now we're on a nosedive in terms of land area change. So, and this map just kind of shows what these wetlands theoretically looked like in the 1800s, and then they've just slowly been basically dissolving. And then this is an old slide, but this is back what someone projected for 2020 several years ago. And so it's a big problem down here because in addition to fish and wildlife and, all the ecological issues that this causes, our economy, both at the state and the national level, is dependent on these wetlands. Commercial fishing, there's a good chance if any of you have had shrimp in the last week that they came from Louisiana waters. The gas in your car may have very well been refined in Louisiana oil refineries or even extracted in Louisiana. And all the oil and gas infrastructure down here has been engineered to be in protected water environments and which are low energy with small waves and things like that. But as the landscape begins to open up like this, these environments become more energetic, and that's going to probably cause down the road more oil spills, pipeline breakages, and things like that, and possibly disruptions to the national fuel supply, which is pretty much a national security issue. So,
Hey, Greg, we have a question.
yeah, go ahead.
So, are you saying that the same amount of sediment is still moving through the river channel, but it's just dumping right into deeper waters, or is the sediment amount that's moving down the river being depleted?
Well, it's actually both. That's a great question, and I kind of brushed through that. Yes, the sediment that is coming down is now being discharged largely out of the mouth of the river down here and into 2,000 feet of water, where it does us no good. But the sediment supply coming down the river over the last 100 years has diminished substantially too, and that's primarily due to the placement of locks and dams along the middle Mississippi River. Up around Iowa, Illinois, down to St. Louis, maybe a little below that. And basically, that area of the river is no longer a lodic flowing situation. It's basically a series of pools that are separated by locks. So a lot of sediment settles out in those lock and dam systems and never even makes it down here. So that we'd probably be having problems like this regardless, but sending them off the mouth of the river is definitely into the deep Gulf of Mexico is definitely not helping. So.
Good question. Anyone else have a question at this point?
For the data of where the land mass was for 1839, where are those numbers coming from?
Oh, like these?
Yeah.
Where did these data come from?
Yeah.
That's a good. This was put together. So there's some old charts of. They're basically hand-drawn maps that people have got their hands on and just tried to digitize them. This is by no means. Obviously, we weren't flying satellites around in 1839 or anything, but these are best estimates of based on some old navigation charts and stuff from back in the 19th century.
Anyone else?
Anyone else?
I think we're good for now.
Okay. So I mentioned river diversions. One of the things they're trying to do, they have done to try and mitigate this problem of these large areas being isolated from river sediments now, is to put some of those sediments back into those areas. And so in 1991, the Carnarvon freshwater diversion shown right here was put in place, and that discharges about 8,000 CFS and any sediments that are carried with it. And that's been operational since 91. And then in 2002, over here in the lower right, the Davis Pond diversion was put in. And it's about the same size, 10,000 CFS, I think. And these things were designed to, they weren't designed to be sediment diversions. They were designed to regulate salinities in these estuaries for oyster fishermen, but we discovered that they also carry a lot of sediment and could be strategically managed, perhaps, to help offset coastal land loss. And additionally, so those are about 10,000 CFS diversions, but there's two 75,000 CFS diversions that are well into the planning stages right now to basically try and mimic this on a very large scale, specifically for offsetting coastal land loss.
What's the increment on the CFS? Are you saying yearly?
That's their maximum capacity.
Oh, okay.
That's their maximum discharge capacity. Great question. And so this one, I'm going to talk a good bit about this one today. This is the Mid-Barataria diversion. I've been very involved in that. And this is the Mid-Breton diversion. This one's probably about 2 years behind the Mid-Barataria one in terms of planning. But here's what one of these looks like. Whoops. This is the Carnarvon diversion, and this is the Mississippi River, just the edge of it, and the bottom of the slide. And this is the levee right here. And basically, they just build a bunch of pipes that go through the levee and flow through to the other side. And you can see there's a nice current coming through here. And in terms of delivering sediments, we know that they work because this is from 1927, which was one of the biggest floods that ever happened on the Mississippi River, and they almost lost New Orleans during all of this. And in an effort to save New Orleans, they actually blew a hole right where the Carnarvon diversion exists today to turn some of this river water loose and relieve pressure around the New Orleans area. And this thing was discharging for about 3 months, a little more. It reached 9,200 cubic meters per second. I think that's about 3,000 CFS, 300,000 CFS. And it discharged an estimated 52 million metric tons of sediment into the area. And if you take a core in the receiving basin of that big 1927 diversion, you can actually see that layer, and the top of it's right here. This is all river clays that were deposited. The top of it's right here, and the bottom of it's about 25 centimeters below it right here. And all that happened in about 3 months. So we do know that they can divert a lot of water and result in a lot of sediment deposition and creation of elevation capital. And so, but I mentioned earlier, there's two drivers of vertical accretion in these inactive deltas. There's the direct deposition of mineral sediments entrained in river flow, and then there's the organic soil production brought about by plants. And so we can take a core and section it into a bunch of different sections, and then analyze each one of these cores, or each one of these core sections, for percent organic matter, bulk density, and then kind of most importantly, cesium-137 activity. And cesium-137 is a radioisotope that is not really naturally occurring, but became present in the atmosphere once hydrogen bomb testing started in 1954. And hydrogen bomb testing peaked in 1963, and then it was banned. And so you can analyze these for cesium activity, and where you see the peak of cesium, which is right here, you know that layer of soil was laid down in 1963. So from all this data, we can estimate vertical accretion rates and also mineral and organic mass accumulation rates, and then look at which one of those mineral or organic accumulation is driving the vertical accretion, just with a regression. And so this is what we've done for all of these cores we collected in Breton Sound. And this is the mineral or the inorganic portion. So this would be the stuff brought in by the river, and there's really not a relationship there. But if we look at the organic matter accumulation versus vertical accretion, we see a very nice and very steep regression curve. Excuse me. So this indicates that in these regions that have been abandoned by the river, it's the plant productivity that is driving the vertical accretion, creating the elevation capital, and allowing these wetlands to do their best, at least, to maintain their position in a rising tidal frame. And so after Hurricane Katrina, we created a land loss map, and the area lost as a result of Katrina is shown in the red. The green arrow is where the Carnarvon diversion comes in, and a lot of us started scratching our heads when we looked at this, because this is all this area floods from the Carnarvon diversion, and a lot of people started saying that maybe this thing had some unintended consequences, and we need to start looking into it. So we looked at the wetland hydro period. So this is just the percent time flooded that the percent of the time that these wetlands were flooded during each growing season from 1997 to 2005. And what we see is that early on, they weren't flooded very much, but then beginning in about 2000, they were flooded 60% of the time, up to almost 90% of the time for several years in a row leading up to Katrina, which happened at the end of 2005. And if we looked at the river diversion operations, and this shows the days that the discharge exceeded about 4,000 CFS, and we chose 4,000 because we know that that's about the inflow rate at which we begin to flood these marshes. We see a very similar pattern. So a lot of people started saying, maybe we've been operating this thing in such a fashion that we're causing more damage by the flooding to the plants than we are doing good by introducing these river sediments. And so we kind of started poking around at some of this, and we looked at during the 2010 oil spill, Deepwater Horizon spill, they opened all the river diversions wide open in basically a futile effort to try and create some sort of outflow situation that would prevent the tide from bringing the oil into the estuary from the Gulf. And it didn't really work, but it allowed us to look at, we had got this long period. So this is diversion discharge showing up on the top figure. And then we've got these, a handful of monitoring stations where we monitor water level. And these are shown by these colored lines down here. And you can see that the one up near the diversion, basically near the diversion, there's a big flooding effect, and it begins to dampen as you move further out. The water begins to spread out and such. But we just sort of made a back of the envelope graph or a figure out of this. I basically took these water levels here and just kind of contoured them and created a cone just to see how far out the color indicates water level. And you can see that down to about here or so, we're inducing 1.5 feet plus of flooding on these marshes with these large river water releases. Well, we also took an airboat across these marshes and collected water samples and analyzed them for suspended sediments to get an idea of how quickly these sediments were falling out. And so this is a plot here of distance down this transect versus sediment concentration, and you can see they settle out very rapidly. And so we contoured that too. And I placed a little white semicircle around the contour that illustrates where we're at 50% of the sediments are already deposited in this little white area right here. And if you overlay the water level response on top of that, what you see is a very large area that's being flooded, but it's not really receiving a substantial amount of sediment. So this suggested that we were actually possibly flood stressing a lot of these plants, but weren't necessarily providing those wetlands underneath providing the soil underneath them with sediment by which to increase their elevation. And so we wanted to look at what this flooding may do to these plants. So we use these things called marsh organs that were developed by a coastal ecologist named Jim Morris at University of South Carolina, and they're basically designed to simulate flooding at different levels, and they're just planters. So we take these things out to the marsh. Oh, I'll get to that in a second. But so we selected 6 rows that were designed to simulate flooding at 10, 30, 45, 55, 70, and 90% of the time. And we just selected pipe elevations based on some previous water level data. We constructed an exceedance curve for those hydro periods of those percentages I just mentioned, identified where those elevations were, and then situated the pipes so that all these elevations were achieved in the field, and hopefully we'd see flooding rates that were in the ballpark of what we were trying to hit. And so we looked at 2 plants that are in this area, Spartina patens on the right, which is kind of a widespread brackish marsh species, Spartina alterniflora on the left, which is more of a salt marsh species we find further down the estuary. So this is our Spartina patens site here, and then a little further down we've got Spartina alterniflora planted in these marsh organs. Let's see. So these just kind of show, these are just kind of fun to look at. This is us putting them out in the field. We get them all leveled in, and then we'd start filling them with mud from the pond, and then we'd plant them with vegetation we harvested on site. And that's a finished product right there. And then so we put these out in March at the beginning of the growing season. slap a water level recorder next to them, so we had continuous water level data, so we could assess flooding. And then come back in October and harvest them, and then take them to a lab and analyze them for biomass. And what you can see, this one in my left hand here, that comes from the highest row, and the one on the right came from the lowest row. And they're all laid out on the bow of the boat right here. And so, working up the numbers, I'm not going to get into all the details here. Basically, we've got Spartina patens on the left, alterniflora on the right, and above ground productivity on the top and below ground on the bottom. For Middle Breton Sound in the blue and Lower Breton Sound in the red. But the point is that you can see that these things don't do near as well when they're when in extreme flooded conditions. And so we have some pretty concrete evidence that excessive flooding could be a problem for these things. And we designed this study so that the results could be used. A lot of people are trying to model this, and we designed this study so that it would be readily integrated into the findings, regression parameters and such would be readily integrated into some of these models that were being developed. And so I want to get into now, and I'll come back to these marsh organ studies, but this mid-Barataria diversion project is underway. Well, it's not being built right now. It's in the planning stages. Right now, the State Restoration Authority, that's CPRA, the Coastal Restoration Protection Authority, actually has to apply for a permit, just like someone building a shopping mall would have to. They have to submit an EIS, which will be evaluated for compliance with a whole bunch of stuff. Marine Mammals Protection Act, because we've got a lot of dolphins in these waters, and these diversions are going to alter salinity substantially in these estuaries and may force these dolphin populations to migrate. Commercial fisheries with the Magnuson Act, basically we've got to be compliant with that, which basically says we can't adversely affect commercial or recreational fisheries with this. 408 permit, which basically means it's got to be compliant with larger existing federal projects. In this case, the big federal project is a flood protection system and navigation on the Mississippi River. And then the 404 wetlands permit, which is kind of where I come in. And that's so 404, that's the Clean Water Act. And basically, there can't be adverse impacts to the existing wetlands that are in the area. And the signatories on the permit, the people that have to approve this thing, are the U.S. Department of Agriculture, the Environmental Protection Agency, NOAA, basically National Marine Fisheries Service, which is part of NOAA, and the Department of Interior, which is again where I come in. So I'm acting right now as a science advisor to the Department of Interior, who has to review all the materials that the state CPRA submits to them, which includes a bunch of stuff related to modeling outputs and parameters that are in that model. And so I've served sort of in an advisory capacity to say, yes, their model incorporates all the latest literature and findings that we know of, or no, they overlook these kinds of things that should be included in their model that aren't, et cetera, et cetera. So, and going back to the flooding issues, this is a big deal because this is sort of a rough outline of what a lot of the hydrodynamic modeling output indicates will be flooded by these wetlands. So this is a huge area. I mean, this transect I'm doing with the cursor right now, that's probably 10 kilometers. And it's probably 30 kilometers wide. And all of this is expected to be substantially flooded, and all the wetlands, and particularly the plants, are expected to be substantially flooded by this. And what we're scared of is that, 10 years after this thing becomes operational, a Category 3 hurricane goes right over it, and we see something like this again. but over here on this side of the river. And we really need to make sure that that doesn't happen, because these projects these are $5 billion worth of diversions, and we don't want to pay $5 billion just to end up doing this. So, I'll just kind of finish up here with a little bit of how our research findings are being incorporated into these modeling efforts, which are being used to try and get the thing permitted. So on the right, we have this, I showed this a few slides ago. This is just our findings from those marsh organ studies. And on the left, what we have are simulations that the state ran with their existing models to try and replicate what we found here. So both of these cases, you've got percent time flooded on the horizontal axis and biomass on the vertical axis after a growing season. And again, we saw serious declines in production as percent time flooded increased. But the initial crack at the modeling performed by the state showed basically a flat response. This plant species was essentially completely insensitive to flooding whatsoever. So we had to work with them to refine some of their model, some of the parameters in the model, basically through kind of a sensitivity analysis, to get this model to resemble. And this actually just happened. They just finished this. We just had a final meeting about this like a week ago, and so they tweaked some of their model parameters, and now they're showing something. It's not perfect, but it doesn't really need to be perfect. It's just got to be qualitatively similar. And they've shown now that their model predicts a decline similar to what we observed in the field. And that's important because, so what the models do is at the end of, they run them for like 50-year projections. And at the end of each year, the models assess how much biomass is in the landscape, and then that feeds another portion of the model, which drives the vertical accretion or the elevation capital, and basically predicts whether these marshes are going to be able to keep up with sea level rise and stuff like that. So we've got them hopefully on track to produce something that's a little more realistic than kind of the path that they ended up embarking on initially. So hopefully down the road then, if this project's implemented, there won't be any surprises because the model will be considerably more accurate. So in addition to this mid-Barataria diversion, which is right here, there's several of these things that are still being kicked around. The state's backing off of a few of these, but anyway, you can still see there's 6, 8, or 10, I don't know, 2, 4, 6, 10 of these things being planned as part of the state's comprehensive restoration plan. So it's really important that we get these predictive models right, because well, in addition to the sustainability of the landscape, there's billions of dollars potentially tied up in all of this. So we don't want to spend it on stuff that's only going to exacerbate the problem. So to close, I usually try and close with something positive, but with each of these new sea level rise scenarios that keeps coming out, it's becoming harder and harder to do so. The worst case, the intermediate sea level projection now is 4 feet by 2100, and worst case scenario now is about 6.5 feet by 2100, and it's just hard to imagine how we can engineer our way out of that. And just to give you an idea of what 6 feet of sea level rise looks like in Louisiana, this is what it looks like. Anything that's blue is water, and you can see this dotted yellow line is basically the current boundary of the state's wetlands. And so we've got a daunting task ahead of us, and but these river diversions are really probably our only shot at it. So with that, I'll take any questions, and thanks so much.
It's great. Yeah, we have a bunch of questions. Go ahead, Josh.
Great.
So I got a quick question, but how as easily as you can, did you all determine where to put those diversions? I'm assuming it's to try to distribute the sediment so that you don't have those washout scenarios like you did with the Katrina example?
That's a great question. In fact, so they've learned a good bit from that. You know, I kind of maybe didn't present some of the state's modeling in maybe the most positive light, but to be fair, the ecological modeling is, the ecological part of that modeling, it's really tough. But the hydrodynamic modeling, where they're, you know, looking at water flow and velocities and sediment entrained in those flows and stuff, is actually state of the art, and it's really good, and it's probably dead on. And they're doing modeling not only in the bayside part of the system, in other words, the wetlands that the diversions are going to go into, but they also do a lot of modeling in the river itself. And they've been using these models and extensive data collection to try and find areas where the concentrations are rich. In other words, where they can divert the least amount of water, but get the most amount of sediment out of it. You know what I mean? So that maybe if they place a diversion, if they want to divert, you know, 1 million metric tons of sediment a year or whatever, if they advantageously select a site to pull that water from the river, they may be able to do that with half as much water, and therefore half as much flooding. And that's something that didn't go that's something they didn't account for with their first two little diversions. The Carnarvon and Davis Pond diversions were not selected based on that at all, but that was the primary driver in selecting where these big diversions that are being planned were going to be placed.
I have a follow-on to that. So in addition to placement of the new diversions, is there anything new about the engineering of those structures that captures more sediment, say, from the lower part of the water column? Or is it essentially built very similarly, just a higher capacity?
Well, they've been able to go deeper in the water because of the channel morphology of the river. So these two big ones that are being planned are below New Orleans. And, well, Carnarvon's slightly below New Orleans, but not far. And so the other two are either near New Orleans or above it. And the channel geometry is different. The river's actually much shallower, but it's wider below New Orleans. And so partially by that virtue, they are basically drawing from a region that's relatively lower in the cross section than they were with Carnarvon and Davis Pond, which should result in richer sediment concentrations. Also, because these diversions are bigger, the pipes themselves are bigger, which means not only are they wider, but they're also deeper.
Okay.
So that brings them considerably lower as well. And they're also the old diversions came off the riverbank at like an exact 90-degree angle, and they're orienting Mid-Barataria to come off at almost a 45-degree angle, so that I'm not really a hydraulics guy. You guys maybe understand this stuff more than me, but basically the flow of the water should be faster because of the orientation of the outfall channel, and which also should allow those waters to convey sediments further, because the water's moving faster and it's more turbulent than with the Carnarvon and Davis Pond diversions.
Interesting. Thank you.
Yep.
With the upstream blocks of dams reducing sediment, is there a strategy that you guys are trying to implement to actually increase the sediment in the water?
Oh, that's a great question too. So that's been looked into. I don't think I basically think that it was determined that it was too cost prohibitive to be practically implemented, but for a while there were basically demonstration projects at the existing diversions where they had a dredge that was literally just, it was slightly upstream of the diversion for the sole purpose of dragging sediments off the bottom and creating a sediment plume by the intake structure that would allow them, that would then get sucked through the structure and discharged out the other side. But it was just, you know, it was so it was, you know, there's so much diesel involved in that and things like that it was basically cost prohibitive to do that in any sort of manner or extent that would be, you know, meaningful for landscape restoration.
Thanks.
Would that be something they might consider doing with the larger projects that have like the bigger pipes and the more potential to get more sediment kind of out onto the landscape? Would that kind of offset some of the costs?
That's a good question. I'm not. So that, are you asking? Well, maybe they could do that sediment enrichment with these bigger diversions, and it might be cost effective down there.
Yeah.
Oh, okay. I don't know. I don't know. I don't have any information on that one way or the other, but my gut feeling is that for probably, I haven't heard anything about that, and it's probably just not practical from not only a financial point of view in terms of, you know, it's energy intensive and stuff like that, but the river, I've learned over the years, is a complicated animal, and I don't mean in terms of science or anything, like more in terms of competing stakeholder interests, mainly navigation and things like that. We've had problems. There was another diversion downstream that was basically, there was no structure built. They just poked a hole in the river bank and just turned it loose for a decade or so. And that whole thing was tied up in court for years because the shipping industry was suing because an Anchorage area where they parked big, you know, ocean-going container vessels was silting in, and the Corps was having to dredge it all to maintain it, to make it useful. And anyway, it almost shut that diversion down, and I'm guessing that anytime, I don't think the Corps of Engineers likes to fiddle with the river too much like that, because there's just too many unintended, they find a solution to one problem like what we're discussing here, and they create another one downstream that just turns into a big headache for them. So I haven't heard anything along those lines.
Okay, thank you.
As far as like where these new larger diversions are going in, those flooded areas, who's the property owners? What kind of stakeholders are you having to deal with?
Oh God, that's a great question, and that's like another hour. But but it's a great. So the stakeholders are landowners, and landowners are. Well, a lot of them are private citizens. A lot of them are big oil and gas companies, own just huge tracts of land out here. Commercial fishermen are a huge stakeholder, and they'll probably, even if this thing is permitted, they'll probably find a way to tie this thing up in court forever, because, you know, you put that much fresh water in, and all of a sudden the shrimp that you were driving your boat 10 miles to go catch, now you're driving 100. And but yeah, commercial fishing is a big stakeholder. Landowner, but yeah, just landowners, whether they're private landowners or most of these people that own this land are making money off of oil and gas somehow. Either they own it for oil and gas exploration or they lease it for oil and gas exploration. And if we see a situation like this, where huge areas are are gradually weakened over time due to the excessive flooding, and then another Katrina comes over it and just turns it into open water. I suspect that the lawsuits will be just innumerable over something like that. And so, yeah, it's once that land turns to open water, then open water is public land. So you've got, it's literally like someone took your house from you. If they're going to be suing the state or the federal government saying, you guys did this to me. I used to own 5,000 acres out here, make X amount of money off of it every year, and now it's all gone. And I'm suing you. So,
has there been attempts at purchasing land from private landowners or oil and gas companies, by the state or other entities?
No, I think A, there's no money to do it, and B, that's that's kind of, people down here are kind of, that they're not real receptive to big government, even if they're offering fair market value. They're not real receptive to, the federal government coming in and saying, we want this to be ours now. And some of that's how people are, and it's understandable that that's how people are. But some of that is, I mentioned this Carnarvon. Actually, I got the slide up. I mentioned that where they blew up the levee here in 27, and this community right here, Delacroix, that place got wiped out from them, from this event, and the government told them prior to doing this that they'd make them whole again, and they basically did nothing for them. And to this day, they're just in this whole region because of all of that. There's federal government's not necessarily real popular in these parts, in these small communities down there. So no, there hasn't even been any big buyout initiatives or even kicked around. That's never really, to my knowledge, been kicked around as an option. It would be too much money, I think, even if they could do it.
Thanks.
Sorry, did you have this?
Yeah, I'm just trying to figure out how to pose it. So with the successful sedimentation of these diversion channels and the creation of new wetlands and islands, who has ownership to those?
That's a really good question too. I don't think there's an answer to that. There's, and we don't have any analogs for it, because the only analogs that we would have, I can go back to I'm just gonna go back to the title slide because it's, bear with me. This, almost there it is. So this, what you're looking at here, the mouth of the river, I think, is right here. And New Orleans is over here. And anyway, this is the Atchafalaya Delta. This is actually a distributary of the Mississippi River. It's actually the 5th largest river in the world in terms of discharge, and I bet almost most of you have probably never even heard of it. But it's just a really short river. It's actually where the river wants to go, but we've got this giant control structure up there preventing it from switching course. And this is basically another distributary of it over here. But anyways, this canal right here was dredged in the 30s for flood protection. And then all of a sudden in 1970 or so, they were like, holy crap, we got this little delta building down here. And it's the, I don't know if this is true, but I've heard this over and over again, that this is the fastest growing land area in the world. But so going back to your question of who owns this, all of this area before this even happened was a state wildlife management area. So the state just calls it theirs. When we start building new land in areas that are not in wildlife, that don't happen to be in wildlife management areas, I don't know who owns that land. And that's going to be a big issue too. Or if you have your land initially wiped out because of excessive flooding or something like that, and then 50 years from now, you've got a little delta forming out there. is that your grandchildren's land? Or, you know, those are real issues that we haven't in practice had to grapple with yet, but we are certainly going to, and we don't really have our act together on any of that.
Okay, thank you.
Mm-hmm.
Hey, Greg, I'd like to return to your research just for a little more clarity. What would you have told the folks running Carnarvon to do differently to reduce the plant stress from flooding and prevent so much land loss during Katrina? Would it just be decreasing the CFS load? And then how does that translate to running a much bigger operation and lessons learned there?
Well, all right. Those are man. All these are great questions, and I can usually partially answer most of them anyway. It's a miracle. For the first part of your question related to Carnarvon, what would I have told them? I would have suggested that they don't necessarily back off on the magnitude of the flow, but they focus on the timing and the duration of it.
Okay.
So that, for example, we know that concentrations in the river can fluctuate very rapidly over time. Like usually on the rising limb of the first flood, that's when the concentrations are richest in the river. And that's just because you have all this easily erodible sediment that's sort of sitting as a layer of fluff on the bottom of the river. And so when the when the velocities pick up, it suspends really quickly, and you get this big pulse of suspended sediments that come down the river for, maybe the first week of the flood or something. So, it's those kinds of events that I think should be targeted, and you can see that stuff coming, right? I mean, we know, a month in advance if we're getting a big flood pulse coming down the river. And so, a 2-week-long event that carries a lot of sediments that floods these marshes with 2 feet of water is not necessarily a stake through the heart, but a 2 or 3 month one that lasts half the growing season when seeds are trying to germinate and things like that, and oxygen in the soil finally becomes completely depleted, and then the plants are expected to continue to persist in that situation until someone closes the diversion. That, that's a whole different thing. And,
right.
and so anyways, and what was the second half of your question? I forgot.
That's okay. I just wonder what you've learned about incorporating, the biology of the plants in more dynamic operational decisions, how you would then recommend using that information for running a much bigger diversion.
Yeah, and so what they're planning for these big diversions is like really, really long. They've got this whole trigger system designed by when the river exceeds this discharge, we open mid-Barataria to 50,000 CFS or whatever, and we leave it there until the river comes back down. Well, that's usually those big flood events on the river that exceed, I think it's 600,000 CFS is the threshold. Those last like 2 months sometimes. We're in the middle of one right now that's lasting that long. And
yeah.
And I get that, their goal is to just maximize sediment delivery with this thing. And I understand that. And there's certainly something to be said about that. But you've got two things going on here. You've got biology and you've got basically physics and hydrology and geology going on. And so I think, and it's politically, it's easy for me to say. I'm not in a policy position or anything like that. I'm just a scientist. But I think sometimes I wonder if, this diversion's sort of been sold as it's gonna not only create new wetlands, but it's going to restore the existing ones that we have. And in reality, it may wipe out everything that's in its way in the first 10 years. But then if it's left to run for another, this is a 50-year project, I think, maybe longer. If it's left to run another 40, well, you might see stuff like this coming in behind
Okay.
what wetlands used to be. And I don't know if the general public is really, you know, they're not aware of all this stuff we've been talking about today, you know.
Sure.
And if they see all their wetlands disappear that are there right now in 10 years, the taxpayer is going to turn on all of this. That's my biggest fear. And so I'm all about tempering expectations and saying, you know, these projects aren't for you. They're for your kids and your kids' kids, you know, and just to basically, well, kind of buy them some time and just put them in a situation where they have reasonable expectations where, you know, we can have some detrimental effects early on with the expectation of all the benefits coming, you know, after the first decade or so.
Yeah, okay, that's a really great point, thank you. We're gonna have to leave it there so we can let everyone get on to the rest of their afternoon, but let's thank Greg again. Thanks, Greg.
Thank you, and man, all of those questions were really great, so.
That was really helpful and super informative, Greg. Thank you for making time and
Cool.
putting effort into this presentation.
Anytime, that was a lot of fun. Thanks for having me.
Yeah, give my best to the fam, and hopefully we'll talk to you soon.
Okay, cool. All right, man.
Good to see you.
See ya.